Imagine you are given a data set of the height of men in the US and find that the data is distributed normally with a mean of 68.8 inches and a standard deviation of 2.8 inches. Remember what normal means. It means that our data is bell-shaped with the mean at the peak and partitioned by the standard deviation. My height is about 69 inches. Then what percentage of the population am I taller than? This is the portion of the population I'm taller than. In order to find what percentage of the population this is, I must take the area of the shaded region and divide it by the total area under the curve. In order to do this, we must use integral calculus. However, since we haven't learned these skills yet, we must find another way. Luckily, in the last video, we learned how to calculate the area under a standard normal distribution. A standard normal distribution is a normal distribution which has values measured in z-scores and has a mean of 0 and a standard deviation of 1. Also, the total area under the curve is equal to 1. We also learned how to use the z-table to find the area of certain parts of the standard normal distribution. Now all we have to do is convert our data that has a unit of inches to that of a z-score. Luckily, we already know how to do this. So if I want to convert my mean of 68.8 inches and other values that are some standard deviations away from the mean to a z-score, I get the values on the standard normal distribution. This is no coincidence. The z-score conversion formula is meant to keep the ratio of our original data. This means if I convert my height of 69 inches to a z-score, finding the percentage shaded here is the same as finding the area in my original distribution. Given a z-score of 0.071, I can find the portion of the population that I'm taller than by looking at my z-table. The total area to the left of a z-score of 0.071 is 0.5279. This means that I'm taller than 52.79% of the population. What percentage of the population is taller than me? If 52.79% of the population is to the left of me, then 42.71% of the population must be to the right of me. What is the probability that a male is less than 5 feet tall? Well, 5 feet is 60 inches, and these are all the people less than 60 inches. To find the area, we must first convert our units from inches to z-score. Use the z-score formula, which says to take the data value you want to convert, subtract from it the mean, and then divide by the standard deviation. If I find the area associated with the z-score of minus 3.14, it is 0.0008. This means that if you were to randomly select an adult male from the US, there is a 0.08% chance that he is less than 5 feet tall. This would be considered an extreme case and would fit into our definition of significantly low. Actually, any z-score less than or equal to minus 1.96 would be considered significantly low, and any z-score greater than or equal to 1.96 would be considered significantly high. It's very close to our estimate of 2 standard deviations above and below the mean, or the concept that in order for a number to be significant, there must be less than a 5% probability of it occurring. Here, this 5% is broken into the 2 tails of our graph, each with an area of 2.5%. So what heights would be considered extremely high for the population? Well, we said for a normal distribution, any z-score above 1.96 would be considered extremely high. So what I'm going to do is start with the z-score and work my way back to see what value that would be in inches. X is the unknown value of the height in inches that will end up having a z-score of 1.96. If I multiply both sides by 2.8, then add both sides by 68.8, then I can solve for x. This means that anyone above 6.2 feet should be considered extremely tall. What heights would be considered significantly low? Well, significantly low would be any z-score below minus 1.96. So let's work backwards again and find the height in inches that would have a z-score of minus 1.96. This means that if you're less than 5.3 feet, you should be considered extremely short for this population. We know our data is normally distributed with a mean of 3,152. Then 3,500 is here, and thus we are looking for this shaded region. First, we must find the z-score associated with 3,500 grams. Remember, the standard deviation is the square root of the variance. So the standard deviation here is 693.4 grams. The area to the left of a z-score of 0.5 is 0.6915. Therefore, there's a 69.15% chance that a newborn will have a weight of 3,500 grams or less. What is the probability that a newborn will have a weight greater than 2,511.5 grams? First, we have to find 2,511.5 on our graph. Then shade the area that we are looking for. Next, we convert our units to a z-score, and again, find the area that we are looking for. If there's 17.88% of the area to the left of my z-score, then there must be 82.12% to the right of it. This means there is an 82.12% chance that a newborn will weigh more than 2,511.5 grams. If someone is a genius, they must have an IQ score of 160 or more. So we find 160 on our graph and shade the area we are looking for. Next, we must convert 160 to a z-score. We don't have a z-score of 4 on our table, and that's because the probability is too large. Any z-score above 3.49 is rounded to 1, and any z-score below minus 3.49 is rounded to 0. If the area to the left of my z-score of 4 is 100%, then the area to the right of it is 0%. So our statement reads that the probability of someone being a genius is 0%. But this does not mean it's impossible. It just means that it's very, very, very unlikely. What is the probability that someone's IQ is between 100 and 118? First thing I want to do is find my points on the graph. Then I find the area that I'm looking for. This time we have two z-scores that we must find. The area to the left of my z-score of 1.2 is 88.49%. And the area to the left of a z-score of 0 is 50%. Thus, if I take away 50%, I'm left with the area that I'm looking for. Therefore, there is a 38.49% chance that someone's IQ is between 100 and 118. If you're in the 70th percentile, that means you've scored higher than 70% of the population. First, we have to find the z-score that is associated with 70% of its area to its left. We don't have an exact number, and the closest we can get is a z-score of 0.52 and 0.53, which have areas to the left of 69.85% and 70.19% respectively. So what we're going to do here is take the average of the z-scores. So the z-score that I'm going to use is 0.525. Now we can use the z-score to find what IQ score it relates to. X is the unknown IQ score which is in the 70th percentile, and I can find it by using simple algebra. So if you get a 107.88 on an IQ test, that means you've scored better than 70% of the population.